Hi, I'm Brad Christian T, and I'm going to prove the Langrange's theorem. First, let G be a group of finite orders, and let H be a subgroup of G. Then determinant of matrix H divides determinant of matrix G. In fact, distance between G and H is equal to determinant of matrix G multiplied by determinant of matrix H, where determinant of matrix G and determinant of matrix H are the orders of G and H, and where distance between G and H is the index of H in G. When determinant of matrix G is infinite, we can still interpret this theorem sensibly. First, a subgroup of finite index in a group of infinite orders is itself of infinite orders. And second, a finite subgroup of a group of infinite orders has infinite index. Let G be finite. Consider the mapping golden ratio is to G near G. Divide integral opposite of derivation H, defined as golden ratio is to G implies G. Divide integral opposite of derivation H is to golden ratio X equals X. Divide integral opposite of derivation H, where G integral opposite of derivation of H is the left coset space of G modulo H. For every Y, H is an element of set of G. Divide integral opposite of derivation H, there exists a corresponding Y is an element of set G. So golden ratio is a surjection. From cardinality of surjection, it follows that G divide integral opposite of derivation H is finite from cosets are equivalent. G divide integral opposite of derivation H has the same number of elements as H. We have that the G divide integral opposite of derivation H is a partition of G. It follows from number of elements in partition that the scalar product of G of H equals the determinant of matrix G multiplied by determinant of matrix A. For any group of G, from cosets are equivalent, a left coset of Y of H has the same number of elements as H, namely determinant of matrix H. Since left cosets are identical or disjoint, each element of G belongs to exactly one left coset. From the definition of index of subgroup, there are scalar product of G and H left cosets. Therefore, the determinant of matrix G is equal to scalar product of G and H to the determinant of matrix H. Let G be of finite order. All three numbers are finite, and the result follows. Now let G be of infinite order. If the scalar product of G and H is equal to n is finite, then determinant of matrix G is equal to n multiply determinant of matrix H implies the determinant of matrix H is infinite. If determinant of matrix H is equal to n is finite, then determinant of matrix G is equal to scalar product of G and H implies scalar product of G and H is infinite. Follows directly from the orbit stabilizer theorem applied to group action on coset space. By congruence modulo, subgroup is equivalence relation. The coset of H partition G. Note that reverse caret of G is an element of set G. Determinant of matrix of H is equal to determinant of matrix of H multiplied by G. Since multiplication by group elements induces an injective map, C cancelable if regular representation injective, that is GH1 is equal to GH2 implies H1 is equal to H2. Thus, presuming there are k distinct cosets of H, we have determinant of matrix G is equal to scalar product of determinant of matrix H and K. Thus, determinant of matrix H divides determinant of matrix G. That's all for the Langrange's theorem. Now, Baby Joy Conese and Jethro Orfrada are going to prove the prime numbers. Thank you.
Hello, I'm Jethro Orfrada. I'm going to prove the prime numbers theorem. The prime numbers theorem gives an asymptotic form for the prime counting function. pi of n, which counts the number of primes less than some integer n, legendary 1808 suggested that for large pi of n approximately equal n divided by natural log of n plus b, with b is equal to 1.08366, where b is sometimes called legendary's constant, a formula which is correct in the leading term only. N divided by natural log n plus b, sin n divided by natural log of n minus b, n divided by open interval natural log n square root plus b square root n divided by of log of n, cube root plus or else. Nagel 1951, page 54. Wagon 1991, page 28 to 29. Habil 2003, page 177. In 792, when only 15 years old, Goose proposed that pi of n approximately equal n divided by natural log of n. Goose later refined his estimate to pi of n approximately equal L imaginary unit of n. Imaginary of n equal integral opposite to derivation of dx divided by natural log of x. As the logarithmic integral Gauss did not publish this result, which he first mentioned in an 1849 letter to Encke. It was subsequently posthumously published in 1863. Gauss 1863, Habil 2003, page 174 to 176. Note that L imaginary of n has the asymptotic expansion about of L imaginary of an interval of an approximately equal n divided by natural log of n plus n divided by open interval natural log of n squared plus 2 n divided by natural log of n cube root plus or else. The first three terms has been shown to be a better estimate than n divided by natural log of n alone. Derbyshire 2004, page 116 and 117. The statement is often known as the prime numbers theorem and was proved independently by Hadamard 1896 and De La Bella Poussin 1896. A plot of pi open interval n lower curve and L imaginary open interval of n is shown. The first three terms has been shown to be a better estimate than n divided by natural log of n alone. Derbyshire 2004, page 116 to 117. The statement is often known as the prime numbers theorem and was proved independently by Hadamard 1896 and De La Bella Poussin 1896. A plot of pi open interval n lower curve and L imaginary open interval of n is shown above. For n equal to n, it had been checked and always found that pi open interval of n less than of L imaginary. As a result, many prominent mathematicians, including no less than both Gauss and Riemann, conjectured that the inequality was strict. To everyone's surprise, this conjecture was refuted when Littlewood 1914 proved that the inequality reverses infinitely often for sufficiently large n. Ball and Cosicter, 1987, Haville, 2003, page 19, Swiss, then shown that the first crossing of pi open interval of n minus L imaginary open interval of n equal to 0 occurs before 10 power of 10 power of 10 power of 34. Now known as the Squiz number, Haville, 2003, page 1919. The upper bound for the crossing has subsequently been reduced to 10 exponent of 371. Lehmann, 1966, proved that at least 10 exponent of 500 reversals occur for numbers with 1116 or 1167 decimal digits. Put limits on the ratio. 7 divided by 8 less than pi open interval divided by natural log of n less than 9 divided by 8. Imaginary open interval of x is the logarithmic integral. Edwards, 2001, page 4, and 0.92 less than pi of n divided by natural log of n less than 1.105. 2003, page 186. He also showed that if the lim pi of n divided by natural log of n exists, then it is 1. Haville, 2003, page 186. Derbyshire's, 2004, page 124, statement 1850. Chebyshev also showed that pi of n cannot differ from n slash natural log of n by more than approximately 10%. Is therefore correct only for sufficiently large n. Hadamard and de la Valle Fauci independently proved the prime numbers theorem in 1896 by showing that the Riemann zeta function has no zeros of the form in the sense that no deeper properties of are required for the proof. Smith, 1994, page 128. Hardy, 1999, page 58 to 60. Weiner, 1951, allowed his somewhat vague statement to be interpreted literally. Hardy, 1999, page 34 and 46, and his proof was simplified by Landau, 1932, and Buchner, 1933. An elementary proof was found by Erdos, 1949, and Selberg, 1950. Ball and Cosicter, 1987, page 63. Haville, 2003, page 188. Although an unfortunate priority dispute over the joint work made the otherwise beautiful proof. Hoffman, 1998, page 39 to 41. Derbyshire, 2004, page 125, version of elementary proofs of the prime numbers theorem. Appear in final section of Nagel, 1951, and it Hardy and Wright, 1979, page 359 to 367. As noted by Hardy and Wright, 1979, page 9, although this proof is elementary, this proof is not easy. On the simple trigonometric inequality, 3 plus cos theta plus cos of 2 theta is equal to of 1. plus cos theta squared equal to 0. And now, the continuation of prime numbers theorem will be held by Baby Joy Conese.
Hello, I'm Baby Joy Conese, and here is the continuation of proving a prime number theorem. In 1999, page 58, Havel 2003, page 187, Villavalle Fawcett in 1899 showed that pi of x equals L imaginary of x plus 0, open close parenthesis, x divided by natural log of x constant of negative a square root of natural log of x. For some constant, note 1998, page 381, where x is asymptotic notation in 1901, Koch showed that if the Riemann hypothesis is true, then phi of x equals L imaginary of x plus 0, open close parenthesis, square root x natural log of x. 2003, page 205, which can be written in a slightly weaker form. Pi of x equals L imaginary of x plus 0, open close parenthesis, x 1/2 plus constant. Derbyshire, 2004, page 237 and 242 to 244. The error term in 15 has subsequently been improved to pi of x equals imaginary of x plus 0, open close parenthesis, x exponent, open close parenthesis, negative a natural log of x the power of 3/5. Walfish, 1963, Raysil, 1994, page 56, note 1998, page 382, Derbyshire, 2400, page 244. Engham, 1930, proved the prime number theorem using the identity of Ramanujan. Riemann estimated the prime counting function with pi of n approximate equal L imaginary of n minus 1/2. L imaginary open close parenthesis n exponent of 1/2, which is a better approximation than L imaginary of n for n less than 10 exponent of 7. Riemann in 1859 also suggested the Riemann function R of x equals summation of mean of population values of n divided by n. L imaginary open close parenthesis x exponent of 1 n. Where is the Mobius function? Wagon, 1991, page 29, an even better approximation per small by a factor of 10 for n less than 10 exponent of 9 is the Gram series. The prime number theorem is equivalent to either lim theta of x divided by x equals 1 or lim psi of x divided by x equals 1. For some value of Engham, 1990, page 83, Landau, 1974, page 378 to 388, Ball and Cossetter, 1987, Hardy, 1999, page 26, as shown by Koch in 1901, Havel, 2003, page 205, some limits obtained without assuming the Riemann hypothesis are pi of x equals L imaginary of x plus 0 brackets of x constant minus open interval natural log of x exponent of 1/2 divided by 15. Pi of x equals L imaginary of x plus 0 brackets of x constant negative 0.009 open the interval of natural log of x exponent of 3/5 divided by open interval natural log x exponent of 1/5.